A stack is a linear data structure that stores the data based on the order they were added to the stack. Stacks have two main operations, push and pop. Push inserts an element to the end of the stack while pop removes the last item. This means the first item pushed will be the last one popped from the stack. This is comparable to a stack of heavy books. For example, you can't access the bottom book without removing all the books on top of it. A queue is similar to a stack, but the first item pushed to the queue is the first one to be removed. The enqueue operation adds an item to the end of the queue, while the dequeue operation removes the first item in the queue. This is similar to a queue at a store, where people line up in order and the first person to reach the counter gets served first. An important detail to note is that dequeuing has constant time complexity, meaning it doesn't take longer as the size of the queue increases. An array is a linear data structure that stores data sequentially based on the assigned index in the array. Arrays have a fixed length and the items are stored together as a contiguous block in memory. The predictable representation of arrays in memory make them ideal for quickly accessing and modifying a value located at any position in the array. Arrays have two basic operations. Reading a value requires an index, which is a whole number used to locate data relative to the array's location in memory. Writing is done by specifying an index and replacing old data at that location with new data. Arrays provide random access as opposed to sequential access seen in stacks and queues, eliminating the need to access unnecessary data before reaching the desired location. Lists or vectors are mostly just resizable arrays. They store data sequentially using indices, but can dynamically change their size to accommodate more or less data. Reading and writing data at a specific index has a constant time complexity, just like arrays, but lists can also push and pop items like stacks, making lists a versatile data structure. Items can be inserted or deleted at any index of a list, but these operations have a linear time complexity because every item to the right of the insertion or deletion has to be moved. A linked list is a data structure consisting of nodes and pointers. Each node contains data and a pointer to the next node in the chain. The last node has a null pointer, unless the linked list is circular. Insertion and deletion have constant time complexity unlike array-based lists, but accessing a node near the end of a linked list requires traversing all the nodes preceding it, making it difficult to efficiently insert and delete nodes that are further down the list. A tree is an extension to a linked list where each node can point to multiple nodes, but multiple nodes can't point to a single node. A node is a parent if it points to another node. A node is a child if it has a parent node. The root node is the entry point of the tree because it has zero parents. Every other node in the tree has exactly one parent. Trees are heavily used in algorithms due to the often quick logarithmic search, insert, and delete time complexities that arrays can't provide. They are a common choice when data needs to be sorted and many insertions or deletions need to take place. The most common implementation of a tree is a binary tree, but the binary tree itself has many variants optimized for specific situations. Binary trees have a maximum of 2 children per node, where the left child has a lower value than the parent and the right child has a greater value. A graph is an extension of a tree where there is no restriction on the number of parent nodes or child nodes. In graph theory, nodes are usually called vertices, and pointers are called edges. Directed graphs are graphs that only contain one-way edges. If A points to B, then B doesn't point to A. Directed acyclic graphs are directed graphs that don't contain any cycles. DAGs are quite similar to trees due to this property, and a lot of tree algorithms are compatible with DAGs. Now, the graph has many uses because it is a digital representation of relational data. Graph theory is home to many of the best algorithms, such as shortest path, max flow, shortest circuit, and many more. There are many ways to implement graphs using an adjacency list, matrix, edge list, or even the traditional pointer graph, but these come with their own pros and cons. A dictionary or a map is a data structure that stores data as a collection of key-value pairs where each key is unique and maps to its associated value. Usually, keys are simple data types like integers or strings that can't be changed. Dictionary operations often have a constant time complexity, which means inserting, deleting, reading, or even checking whether a key exists is instant, regardless of how big the dictionary is. Keys provide much quicker access to unloaded data than a linear search through an array, and can even outperform a binary search. The speed of dictionary operations makes dictionaries very versatile as they are not limited to a consecutive set of integers for indexing, like arrays. Dictionaries can replace arrays in situations where data is stored far apart, reducing the amount of memory wasted.